Hi folks, this is the third video segment that I'm making on dynamics in Catia, linear dynamics in Catia. The first one was an overview of what linear dynamics is. The second one, which actually was broken down into two videos, was a mass spring system. And the third one, we now actually create a continuum model. In other words, we're going to be looking at the problem that's shown on the right-hand side. It's a bar that is under a suddenly applied axial load. The load is shown here on the left side, and it's constant. However, keep in mind that a load of 100 pounds cannot be instantaneously applied, and what it means is that it is ramped up very quickly to that value, and as it is, the limit, of course, is zero. Limit of the ramping time is zero. Therefore, this becomes an impact load, okay? And therefore, it is a dynamic problem. Now, the details of the geometry are given here: the length, the cross-sectional radius, cross-sectional area, Young's modulus, and the mass density. Now, we assume that there's no damping present, and based on some simple expressions in strength of material or maybe a vibration course, the speed of the propagation of the compressive wave is given by square root of E over rho, which is approximately 200,000 inch per second. Okay, now this is a stress propagation problem. In other words, as soon as the load is applied, at that instantaneous load is applied, a pressure wave will travel down the path, and eventually it reaches the wall. It hits the wall, and then it gets reflected, maintaining its magnitude, same magnitude, and of course also compressive in nature. For example, if you look at this point in the middle, and this is the location that we're going to be modifying, based on that speed that I have, there is nothing happening. This point, middle point, has no idea that there is a compressive wave coming towards it, and it takes about 0.05 millisecond before actually it sees that minus 100 compressive force, and it stays like that, and until this compressive wave reaches the wall, gets reflected with another compressive load. So now it's 200 compression, PSI compression, and it reaches this point again after almost 0.1 milliseconds. Okay, so the exact stress variation as a function of time in millisecond is given in this diagram that you see here in this red lines. Okay, so no stress, compression 100, compression 200, then compression 100, and eventually it becomes again zero. And this process keeps repeating until well, forever if there is no damping present. All right, so we're going to solve this problem. There's more meat to this problem than the mass spring system, because in that one, although the concepts are pretty much the same, except that there's very limited post-processing capability. I want to show you how you can actually do much more in this particular problem. This particular example was taken from the book by Cook, Malkus, and others, and applied finite element analysis. All right, let's go ahead and make this object. So we go to Catia. We create a line. So on that vertical plane, I will sketch a line which is 20 inches long. I may have to set my units here to the units of this problem. So let's go to Tools, Options. Let's see now, units. Length is going to be inches. Force is going to be pound. Where is the force? Force is going to be pound force. Density is going to be slinch per inch cube. So where is the density? Let's see, the density is right here, and we're going to change it to slinch per inch cube. That's this, okay? And pressure, which is, you know, basically our stress, is going to be in psi. Pressure is already psi. All right. Oh, let's make the time also milliseconds. Where is the time? Okay, time. Let's use milliseconds here. Milliseconds. All right, so let's start dimensioning. This is going to be 20 inches. Okay, exit. Now, what I would like to do is to monitor the point right in the middle. Now, in order to create a point in the middle, what I'm going to do is create a point, and then you have to make sure that that becomes a node later on, and I'll show you how that is done. Okay, first of all, let's do a point. And with the coordinates, the only thing is that y is 10 inches, so it's going to be exactly halfway along this line. Now, we have to make sure that this point actually becomes a node later on, because we're going to need that. All right, let's make everything out of steel, metal, steel on that part. And I'm going to use exactly the same properties that are given in Cook's example. Let's wait for this thing to pop up. There's a slight difference. Click on the analysis tab. Instead of 2.901, we want 3. Instead of this 7.35 slinch per inch cube, we want 7.4. And the Young's modulus, the Poisson ratio doesn't come into the picture here, because we're going to be modeling this thing with beam elements. Okay, so that's good. Now let's save this thing. File, save management, save as, desktop. I have this folder here. I'm going to make it wave propagation. Propagation. Okay, good. All right, now let's go to, if you go to generative structure analysis, we can mesh this thing with beam elements. However, there's no guarantee that this point we can make sure that it is actually one of the nodes. So let's say for now we say static analysis, but I'm not going to mesh it yet. I'm going to go to advanced meshing tools. Okay, advanced meshing tool. Here's the beam mesher. Notice that the beam mesher here, it allows me to do some fancy stuff down there, which was not possible to do it in generative structure analysis. So we select this. Oh yeah, one thing I forgot to do is to join this, because unless I join it, I will not be able to mesh it. So let's go back here, we're back to the part here. So go to wireframe and surface design, or generative shape design, either way. And there's the join, and there's a sketch. Without doing this, actually we cannot mesh that thing later on. If I had created a wireframe, a line, then it would have been possible, but not if it's a sketch. So right here, beam mesher. See, now I can select this, and over here it says that you can pick a node, you can pick a point, and make sure it becomes one of the nodes. Okay, so here is the point. There, here's a point to within that tolerance, which is you can even give it a tolerance. But see, this is a little bit heavier in color. So now if I look at my mesh, definitely this is going to be one of the nodes. Okay, so let's actually go ahead and give it size 2, meaningful size 2. So well, I don't know, I didn't pay attention here. 0.2, that's a lot of elements here. So why don't we make this thing maybe 1? So there is 20 elements all the way through. Okay, good. We're done here. So let's actually save the analysis file, save management. There's the analysis file, save as. You use the default name and put it in the same directory. Okay, good. Now, this is a beam element, and when you have beam element, you have to give it the cross section. However, it is possible to change the where are we? First, let's go to generative structure analysis. Right there. Put the cursor here. Right click. See, it's possible to change the type of the element from beam to bar. There was a video clip that was prepared regarding beam and bars and shells and membranes and things like that. You may want to watch that in case we don't want beam, we want bar. We say okay. Okay. Now that we have a bar here, when we specify the cross section, see that? Well, first of all, let's make sure this is none. The offset is none, because last time that I did, I used offset, so it was still there. So now we're going to go and change this thing to bar. You click on the wrench, and you give it according to the PowerPoint. The cross-sectional area is 1 inch per second squared. Inch second squared, I believe it's like that. All right, what is inch? Sorry, not inch per second squared. 1 inch squared. That's what I meant. 1 inch squared. Okay, that's good. All right, and we say okay. All right, now let's see. Now this end is clamped. This end is clamped. Okay, and why don't we constrain everything to move in the y direction? So user defined, everything moves in the y direction. So this entire thing just moves in the y direction. It's a bar, all right? And we apply a force at this end, 100 pounds. So force at this end in the direction of y, negative y, to be minus 100 pounds. Minus 100. Okay, so actually you can see that there is a force here, right there. Now, this last constraint that I did, actually, yeah, that's fine, actually. Let's leave it the way it is. Good. Now, first of all, this is a simple problem. You have a bar under a compression load, so if you run it, you're going to get a compression, and the value of the principal stress is going to be minus 100. Now, notice that we can plot the displacement, and of course it is correct. You can see that everything moves to the left. All right. It gives you the value of the displacement here, but why don't I plot instead you cannot plot the von Mises stress for bars and beams, but you can plot the principal stresses, and of course, needless to say, that they all look at it, they're all compression, and the magnitude of it is minus 100, as we expect, because the cross-sectional area was 1 inch squared, and the load that we applied was 100. Okay, so my suggestion to you was to always do static problem, because if there are any errors, it's going to, at least initially, going to show up here. Okay, so let us deactivate this plot. All right, the next step is to do a frequency analysis. Okay, so insert, oops, frequency case. Now it says, do you want new restraint? The answer is no. I will use what I have before, the restraints that I had before, which were right here. All right, and that's pretty much it. So let's run it. And get our default 10 frequencies. Remember, by default it does 10 frequencies, 10 of them, okay? And if you want to know what they are, one way to do that is just plot the deformation, double click on it, and select the occurrence. It gives you all the frequencies. These are all the actual frequencies. There is no rotation, there is no bending, because I constrained this thing. First of all, the type is bar, so there is no bending anyways, but anyway, these are all axial frequencies. Very good. So we did the second stage. First was the static, then it was the frequency, and now we're gonna do insert a transient dynamics case. Okay, now it says, do you want the frequency case solution? We already did the frequency, so the answer is yes, we want it from here. These are the 10 frequencies that are going to be used, and load excitation, this is a new, that's fine. Okay, good. Now, okay, first of all, this load, we are assuming that it's a constant load over all times. Okay, so that means that instead of us going and creating an Excel file with the variation of the load as a function of time, we can do a white noise. You click on the white noise, so a white noise modulation is going to be created here. All that means is that the load is going to be constant over all times in the model. Okay, now let's see what else we have. We double click on the load excitation. It says, well, first of all, what is the load? The load, we already have it from the static case. We can go and select it. The same one. The factor is 1. We're not going to scale it up, so it's going to be whatever it was, 100 times 1. And the modulation is going to be this white noise right there. By the way, I could have done an Excel spreadsheet, which is for all time, the value is 100, negative 100. Okay, so we just leave it the way it is. That's why we use white noise modulation. Okay, good. Now, double click on transient dynamics. It says, how many milliseconds do you want to run into? The default is 10 seconds, but if you look at your, if you look at this thing, we are interested only up to 0.4, what is that, 0.4 milliseconds. So let's go to 0.4 millisecond. And let us specify, let's say, right now 100 or 200 sampling number of steps. Okay. The bigger this number is, the more accurate results are going to be. Now, okay, so let's see now. I think we have done everything. Why don't we save this before we run it? And we run it now. Done. The reason it's so fast is that it's not actually doing any time integration. It's not changing time step. It's doing the Duhamel integral calculation. Now, let's look at something here. First of all, let me deactivate this deformation from the modes. If you double click on this, if you put the cursor there, right click and say generate 2D display. Okay, generate 2D display, and then you say next. Let's say one graph. What it's saying is this. Okay, why don't you go and select the node that you want, and because it's bar, by the way, it's a bar element, translation tx, ty, tz. Rotations are not even part of the problem. So what we have to do is we have to minimize this, go and select the node. Now, unfortunately, my nodes are not showing. So, there's the analysis. Sorry, right there. For example, this, let's hypothetically say this node, okay? Or I can actually hide this and select that node. This is the node right in the middle that I made sure it's there. Okay, so add it, and right, so close it. I think I forgot to do something, so actually let me cancel this. I think it is sitting down here. That graph was probably sitting down here, right there. Okay, right there. All right. So this is the displacement. It is the displacement of that node. Okay. Now, which displacement is it? So let me see the legend here. This is node number 3. There is 3 colors here. The only displacement that, of course, is going to pop up is Ty. Okay, Tx and Tz are both 0. Okay. There was no reason actually to plot Ty and Tz. Let's do another one. So I'm gonna close this. I'm gonna close that. Okay. Get back the analysis. Put the cursor there and do another one. Generate to the display. Next, let's say 3 graphs, which means that the displacement, velocity, and probably acceleration. So okay, so let's see now. Finish. It says go pick it. You see that? One is velocity. Let me see. Let me zoom in. Okay, let's go ahead and do it and see what happens here. Right. Graph 1 is the displacement. Graph 2, the one below it, is velocity, and the last one is acceleration. Okay, so now we're going to select that same node. Where is the analysis? Right there. So that same middle point, for example. And there's no reason for us to plot Ty and Tx and Tx and Tz because they're 0. Add, and we say close. This is showing here on the graph. Where is this graph? It must be not this one. Not that one. The one that says RES. It's not this. There. Okay. So you see here is one is the velocity, one is the translation. This is the acceleration, meter per second squared. By the way, we can change these units somehow. We will show you how. And this one is meter per second. And this one is just meter. Now, if you want to change these, let's see now the units, right-click options. Instead of MKS, let's make it options defined in options. So this one becomes inch per second squared. I suppose you have to do these one by one. So right-click options, not MKS, but whatever our options unit was. This is now inch per second. Okay, and incidentally, the bottom axis is millisecond because that's what we asked for, millisecond. And this is this one is a translation, so not MKS option, so that's going to be inches. So you can see that it is inches, and down here is millisecond. All right, good. Now, this is fine, and in fact, I can display the translation, velocity, and acceleration of every node. However, what I would like to do is to get the principal stress, and you can see that the pathway that we followed will not get us there. Okay, it'll just give you velocity, acceleration, and displacement. So here's what you need to do. You go here, right click, say create a local sensor. There was some video segments that I posted on these local segments. So here's what we're going to do: create a local sensor, and what we want is the principal stress. It's useless to do a von Mises stress because von Mises stress is not even plotted, generated for the bar. So principal stress, okay, right there, and we say okay. You might say, well, what happened? Okay, well, look, if you expand this, you see that it's attempting to generate the data. Now, let's do something else here. Right click, update sensor. Right click. Actually, let me do the following. Double click on this. Okay, first, before I say right click update sensor, I double clicked on this line and it says, okay, where is the support that you want to take? Now remember, I can go and select this line, but that's not going to be what I'm interested in. I'm interested in this point. And this is where it was important for me to actually make sure that this point was included. This point could have been anywhere, and I could have included as a node, but that's the reason that I actually made sure that there was a point there which I can use. Okay? There could have been a node there, but that node cannot be selected as a support. But the way I did it, I can select a point, and that point can be selected as support. And we say okay. All right. Now right click, update sensor, and say fine, do it. It's done. Notice that the exclamation mark is done, and now I can go here and say generate 2D prop display. Okay. Now look. Remember, it was 0, minus 100, minus 200, minus 100, and 0. This is supposed to be that curve. The reason it doesn't look like that is that this is an impact problem, and for an impact problem you need more than 10 frequencies. With 10 frequencies, this is what you're going to get, although it resembles that, and the numbers are pretty much the same, except that I have to fix the units here. Let me actually do the units first. I go here, let me see, I think you have to do right click, options, not MKS, the specified things in the option, which was in PSI, right? So look, 0, minus 100, minus 200, etc. So this is supposed to be that curve. The reason it's not is that we need more than 10 frequencies in order to do the problem. So let's go ahead to do the following. First of all, let me close these graphs. I don't want them. These graphs that I generated with the velocity and acceleration, I don't want it. And this last one, I don't want either. So I go to analysis, go back to frequencies right here. Instead of 10, let's make sure we have 30 of them. Okay? You say okay, and run the whole thing, the whole shebang. It's going to do it in one shot. It's going to do the frequency, and then I don't need the static, but I'll do it anyway. It'll rerun the entire thing. Oh, you know what the problem is? We have 20 elements, and I'm asking for 30 frequencies. Okay, 20 elements has 20 degrees of freedom, or 19 degrees of freedom, and I'm asking for 30. So this is why it's not good. So I've got to go and change this. Where is that frequency case? Where is this? Double click on this. Instead of 30, let's make it, I don't know, 19. Because I think this is 19 degrees of freedom. Run it. Let's do all of them. Now I could have made the element sizes smaller and therefore more nodes, therefore more degrees of freedom and more frequencies that you could have asked for. Now here, if I say right click, or if you double click on it, there, see, it's a lot better. See that? It used to be really ugly, Now it's better. So actually, let's do the following. I want to ask more frequencies. However, because of the size of my elements, I cannot ask for more than 19 frequencies. So let's go here to the size of the element, which was right there. Let's change this thing to 0.5, which means I can have about 0.5 will give you 40 elements, and I can go up to 38 frequencies. Okay, so let's go here and do 38, request 38. 30, I'll make it 30 or 35. Run the whole thing, including the statics that is really not necessary. I have to do frequency and yeah, transient dynamics, of course. Good. So let's go here and double click on it now. A lot better, as you can see. Okay. And of course, if I use more elements, I can ask for more frequencies, and this is going to be more in line with that kind of a graph. You cannot get rid of these peaks here at where the discontinuity is. This is called Gibbs phenomena, and every time you have a discontinuity like that, a sudden drop of the load, etc., this artifact is going to be there. Now, there's something else I wanted to show you, and that is the following. Suppose you want to do your own post-processing because this is not acceptable to you. Then what you have to do is you have to import this data. See that? Select data. This is the data that's on the screen. Select data. Right. Let me see. Where's the analysis? Okay, let me do it. Oh, I think yeah. Let's do it a different way. Let me get this plot again. Where is this 2D? Right there. Select the data. All right. Now I'm trying to see how you can export the data. So let's actually do something else here. Let me close this for a second. Okay. Where's the analysis? The analysis is right there. Okay. So let me do another one. Sensor. Right click. Local sensor. Once again, let's do the okay, I think the way if I want to generate this data and take it to some other program, what I need to do is the following. Let me delete this. Forgot about this. Okay, so okay, right. So here's the situation. You plot the principal stresses right there, and you say when, at what time. So for example, or let me see for a second here. Double click on this. So 0.1. Well, okay, 0.1. Okay, and then right click export data. It says where do you want to put it. So let's say we put it on the desktop in the Excel format, and I give it a name. This is the name, except that I don't want to call it displacement. I want to call it something else. My data. Okay. Okay, so we go here. There is the spreadsheet that was generated, and what it what this thing gives you is at that instant, which was 0.1, I think it was 0.1 millisecond, all the nodes and the stresses. Well, there's only one stress here. It's the principal stress, okay? And the velocities. Okay, these two are actually not used by me. I didn't even ask for it. I don't know, for some reason they're generated. So I mean, if necessary, you can delete these things. I have to go back and see what is it that I didn't need to do. Okay, delete. All right. So you can generate this. Now this is the variation as a function of nodes. Okay. So I mean, you can go and plot it, but this is in case you want to do further processing, okay, which I don't want to. Hopefully this became better. You can do more processing if it's a continuum model. We'll do some more exercises later on, some more tutorials later on.